As was mentioned, I am mostly known as Funky Bob around the place. If you see me online, that's the name you'll see. I've been using Python since the late 90s, and 1.4, 1.5. I've been using Django for most of that time. Yeah, and my slides are falling off the bottom. That's not good. I'm not going to go for a very deep dive into how peg parsers work and why they're brilliant and all the rest of it, because this guy, Guido, someone, has done a much better job than I ever will. He gave a talk at North Bay Python, which is well worth your time. He's done a long series there. There's a link there on Medium explaining his integration, his dive into peg parsers and why he replaced the parser that's in Python with the peg parser just a few years ago. Just a quick refresher on the process that parsers typically go through. Anyone here got a lot of background experience with writing and using parsers for language? A few of you, okay. Nobody's really had that strange occurrence with Lex and Yak and tools like that. A few nods here and there, yep. Don't mean to cause any flashbacks. So typically you start with your code and you feed that into the scanner. This bit will recognize individual characters and build them up into tokens of some description. And then the tokens get fed through into your parser, which is what understands the syntax of your language and enforces the rules on that level. And then the parser generally builds some sort of abstract syntax tree, which is then fed to the rest of the compiler to turn into whatever code is executable. What is a peg parser? A peg parser works from a parsing expression grammar. It's a way of describing the syntax and understanding it in a much shorter way. It was introduced by 2004 by Brian Ford. That's a link to his paper on it. And right from the outset, it starts dog fooding. So this is the peg syntax described using the peg syntax. It looks a lot. Anyone who's worked with EBNFs or read any RFCs, you typically be familiar with this kind of structure. Very similar syntax, but has some interesting special qualities. Notable differences from those sorts of context-free grammars. Firstly, as an advantage, it's scannerless. It doesn't have that first stage of tokenization. It's able to tokenize and construct syntax or analyze syntax in one pass, which just makes things a little bit easier. It has the advantage of being unambiguous. There is only one way that a peg parser will interpret any given document. It is simply because the first match wins, which is something we have to pay attention to later on, but we'll get there. Yeah, it doesn't require that separation of stages, no compilation, and because it's compatible with pack-rat parsing, which is a special way of memoizing your solution as you go along to find your matches, you can actually typically amortize your costs down to linear time, as opposed to some other solutions can get into pathological cases that just explode. On the disadvantages, it tends to use more memory. Because pack-rat parsing is memoizing a lot of things, you often wind up with a lot of extra memory for paths that you've taken and not gone down. And there's this issue with left recursive rules. So typically, if you think of your regular mathematics, you might have the ability for what's on the left side of your expression to actually expand into more things down on the left side of your expression and so on. And you can't do that in pegs, but that's okay. There's ways that you can avoid that in how you describe things. A quick overview of key points of the syntax. You'll have an identifier and an arrow pointing to it saying this is described this way. So you can have literals, which can be either a literal string or a range of characters. You can say that an identifier is another token or maybe a token if you've got a question mark, or one or more of this token. If you've got a plus, it's very regex like that, or zero or more of the token if you put an asterisk. You can have compound tokens to say that this next part of the sequence must be these two tokens together. Then you have choices where you'll go, as I said, first match wins. So you put your most specific first, and then maybe this, or maybe that, or maybe the other. you can then combine some of these and have, well, I mean, one of these two symbols may appear before my token, and that's how I'm going to parse it. You can also have look-aheads, and you can say, this must happen after this token, but don't consume the next thing in the path, just it must come next, or it must not come next. And finally, you can have repetitions, which is to say, this token must appear this many times, or between this many and that many times, or at least or at most this many times. So the peg parser, harken back to the view I showed before, you take your code, you feed it into the parser, and you build your AST. We've saved a step. It's a little bit easier. And I found in using this, it was much easier to reason about in doing that because you can construct all of your system in one expression. So Parsimonious is by Eric Rose and a bunch of other people helping. I want to try and show the fact that they too did we not get that? I can't actually, yes. It didn't went to the right line, and I've got the wrong glasses on. Partway through in their description, they actually have their own language described in their own language. And so to get started, there it is. They describe their parser in their parser, and then have a bootstrap parser to build their parser to parse your grammar. All right. So they're focusing on making it fast, and I've certainly had no issues there. Frugal RAM use, minimalistic and understandable idiomatic Python, so that we don't have to completely change the way that we're coding in order to use it. Make it readable and extensible. It's got excellent test coverage, as they describe in the documentation. Everything that's written works. Everything that they provide in the package. Separation of concerns, in as much as they do the parsing and hand you over a tree, and that's it. They don't try and turn it into code. They don't try and be a complete package. They stop at the boundary of their responsibilities. And good error reporting, they will tell you where the error happened or where they got up to with pretty good accuracy. So, let's try an experiment. Let's try JSON. Now, that's why I have this page up here. If you have a look on the right-hand side, you'll see that there's a description there in something looking like EBNF of how JSON interprets numbers. This is how you would write that in Parsimonious. And have I chosen the wrong colors? Is that readable from the back there? It's all good? No, not great? Sorry about that. So on our first line, I can get my mouse there. I can highlight it. Okay, so our first line says that a number is made up of either an integer, a fraction, and an exponent, or an integer and a fraction, or simply an integer. And an integer is a minus and 1 to 9 and then multiple digits, or a minus and a digit, or 1 to 9 and multiple digits for a single digit. So something I learned whilst preparing for this, JSON does not allow numbers that start with a 0. There you go. So there's a token there for how do we describe digits 1 to 9, 0 to 9 and 1 to 9. We're just using a regex expression. Parsimonious has its own special syntax for that. The fraction is a dot followed by multiple digits, or 1 or more digits, and then exponent is an E, lowercase or capital, with a sign and the digits. All right, but what do we get for that? What comes out of having used that? We get a tree. Now, it's not a binary tree, it's a tree of nodes that is matched. And you'll see at various points in the tree, we have nodes that are actually labeled with the tokens that we've described. So we have our number and our integer and a 1, 9 digit. And then some of them are intermediate nodes to say, well, yeah, we matched those things and then we produced something that was a 24 or 24.96 and so on. One of the advantages of pegs, because that's merely a literal translation from the EBNF, is we can actually simplify this somewhat. So instead of saying, well, we've got three different ways of describing the number, actually, well, a number is an integer, and then it may be followed by a fraction, or it may be followed by a fraction and an exponent. And then the integer is maybe a negative, and then some digits 1 to 9, and then a digit, or maybe a minus with a digit after it. So we managed to compound those breakout of choices down to 1 to 2 terms. And the exponent, we can say, well, either it's lowercase or an uppercase e, followed by maybe a plus or a minus, and then a digit. Does this really change what we get out? Not in a very obviously noticeable way, but you will notice that the level of nesting on the right-hand side is a little bit flatter than what's on the left-hand side. This becomes important later on when it comes time to turn this into our AST. So, again, what does actually all of these tokens mean? We can see here that it's gone and matched the fraction, matching 0.96. That's our fraction term there. And an integer matching 24. And our exponent did not match anything. So it's there at the bottom. I really wish I had my laser pointer today. And so the whole term that we've parsed has matched as a number, and that's the term that it's matched. So running something through this particular parser, we can at least come out the other end and guarantee that it is a valid number in JSON. Next step then is to walk the tree. Now, Parsimonious introduced a node visitor algorithm for doing this. You write a class. They do note that technically there could have been all class methods, but that would have just cluttered up the declaration as you're going through, so it doesn't really matter. So what's going to happen is the node walker is going to visit all of your nodes depth first and look for a method matching visit and the name of the node type that you've described, and hand you over the node that it's reached and all of its children that have already been visited. And you get to decide what to transform that into in your tree. So for example, we might simply say, look, I'm not interested in grabbing all the little pieces down below. I just want to get to, I've parsed a number, and then I'll deal with that. So we write visit number, and the node.text is the actual text that our node has matched. If we wanted to, we could visit all of the children and go and see what's going on there. I left off the comment there, I'm sorry. So, we have some choices and trade-offs to make here. Okay. So, why would you choose one of those two syntaxes over the other that I showed before? Because I had the long form with the 3 different choices, or the single compact form. And the main difference is the first form produces something that's much more easy to feed to match in Python, match case. Are we familiar with the recently added match case structure matching? So you see here, we get a number, and the structure inside is flatter and more consistent, but you will see that the number of nodes involved and the number of wrapper nodes involved actually pretty much matches the number of terms and operators that you'll see in the grammar. So where we have integer on its own, we get back one node number, which contains one node integer. Where we have integer and fraction in parentheses grouped up like that, that's the second case. We get one node number, one node what was matching, and then 2 nodes inside of that, because that second level node is the grouping, and then the ones inside of that are the actual terms we defined. And then the third case is there. So you could write a match case like this and be able to say, well, whatever I was handed, I know it's going to be one of these three shapes. Whereas the second form, because of all those different operators we've got involved now, tends to produce much more nested and complex outcomes. That sounds like a bad choice, because now we've got all these different shapes and it's not as easy to work with. However, when you start introducing other sequences, such as if we are allowing you to sum numbers together, well, then we're going to be repeating number, operator number, operator number, operator number multiple times. We start getting a much more regular shaped structure. So we have the number that we've matched, and then we have these regularly shaped operator number that we can iterate over and say, okay, let's compound our expression out of these. I'd now like to jump to some code I prepared earlier. I, in my day job, was tasked with producing a system that allowed users to write surveys. And those surveys would have conditional expressions in them, so they'll allow them to say, well, if you answered this, you don't need to answer that question, or we need to calculate some things along the way based on your answers. And I didn't want to hand the front-end users Python, because as easy as that would have been, firstly, they're not programmers, so I don't want to have to give them a programmer-designed language where you have to think too much. And I didn't want to have to lock it down. Locking down Python is a fool's goal. So we developed what we called Quandary, which hopefully will be open sourced soon. This is my grammar. It took a while to develop, but actually in the end it became quite familiar and quite simple to work with. We have a string type, which is simply quotes until another quote. We have Boolean, which is either literally... I thought I'd put this up here. I'm sorry. I didn't think this clearly. We have the Boolean. We have numbers, which are simply defined as might have a minus in front, and then some digits, and maybe a dot and some digits. And names, which are simply A to Z repeated. A to Z at the front, and then one or more word characters. A lookup is described as a name, and then maybe dot and another name, and then that can keep going on. Again, that splot operator to say repetitive. We'll skip over the conditional stuff for now. A function is described as a name followed by parentheses and then maybe some arguments. And arguments are described simply as an expression and maybe a comma and another expression on forever. This is where we start getting into order of precedence. We could have, as I did earlier, have all the operators on one line and simply say, well, we'll figure it out somewhere. When we get a multiply, when we get a plus, when we get a whatever. That doesn't work, or that causes us a lot of work later on. So instead, we say a power expression is a term with maybe a, why is my cursor not be here, please? Thank you. Now, OWS is optional whitespace. This had to be introduced because of, I will explain, a rather annoying bug that we discovered through faker testing. Then we go up a level. So a factor expression, which is producing either a multiply or a divide, takes a power expression as an input. Now that might be something raised to a power, or it might simply be something with no power appended because that's optional. And then a sum expression has to derive from a factor expression, and then a comparison expression has to derive from a sum expression, and then an inversion, again, and a logical expression is either a not expression, and then maybe a Boolean operator, and then another not expression. So this layering allows us to enforce the order of precedence in evaluation of our language. But we'll notice here, our top level is an expression. And then down here in term, everything, so power expression can take in expression, where did it go? List, which can be a single thing. It ends up being cyclic, so that what comes in the top can go in the bottom if you wrap it in parentheses. And this way we get, again, an order of precedence by you can wrap things in parentheses, and then your expression can go in there and then be treated as a term coming into the bottom of this list again. We did have function calls. We have two different conditional syntaxes, so that you can either say, well, it's sort of a ternary expression like you're familiar with, or you can say, use this value if this expression is true, else use this value if this expression is true. It's allowed people to write something that made sense to non-programmers. Okay, well, what do we do with this? Here is my tree visitor. I ended up finding it very useful to have this is blank, because there's two different ways that the system would tell you that you got a non-match. You might get an empty list, or you might get a node that whose start and end matched. So I wrote this little helper for it. So if we start down the bottom, when I visit whitespace, I return none. I'm not interested in whitespace. And same with optional whitespace. If I visit a string, I'm going to construct an AST string class, and I'm stripping off the quotes. If I visit a Boolean, I'm going to construct my AST Boolean class from the text. Numbers, names, all very much the same, because that's all they are. They are single token constructs. When we get to a lookup, this is where things start to break apart a little. So we've been passed all the visited children. We're not interested in the node itself that we've been given, so I ignore that here. And I'm going to say, I know my first node is the arguments, and then if I've got more, that will be the second part of the visited children, which is that collected group. And then I'm going to say, well, if it's not blank, I'm going to iterate over those sets and keep appending that list of names, because it was name dot, and then construct a lookup from those arguments that was given. Comparison operator, we actually just take the operator out of the token, just get the operator we matched, and that's all we need for now. Same with all the other operators, because life gets really simple when you live in Python land, as I'll show you in a minute. We can construct a list by doing the same thing. Now these discarded parts are because the start of a list is parentheses, optional whitespace. I don't care about those two, I'm going to throw them out. Then my arguments, and then closing whitespace. And then I'm still going to iterate through those and turn them into a list of arguments from my list. If we get parens, that's producing either a list or a function, or nesting the group of an expression. So I just pull the expression out of the middle of it and keep going. I did originally write a lot of this using match case, but later on found that it was very effective for some conditions and tended to just clutter things for some of the more complicated situations. This is arguments in a function. Again, the same pattern keeps recurring of, hey, did I get anything more in that splot expression? Yes, let's iterate over it and construct out the things we want. If we get a term, we just want that term. Just whatever the first thing that came through for that term, we'll take it. Power expression, again, the same functionality over and over. Now, most of the so generic visit you must write yourself. They say in the code that there is no logical common default for this, so you put it yourself. Now, what I used this to do was to say, I'm going to take all the visited children, unless they're something I've said I'm not interested in. Well, it's just such as the case of optional white space and so on, where I'm returning none further down. Producing a conditional ifs, they're a little fiddly. We'll just go on to the conditional rules. So we've gone through all the operators. So most of the rest of the work actually happens in this AST module, which is not using Python AST. I had considered that as probably more work than it's worth. Instead, I created an AST class. A lookup just takes the list of arguments it's been told, and then later on I say, when it's time to evaluate, pass me my scope, and I'm going to run through everything and ask my children to evaluate themselves, resolve themselves, and pop it out. Then we have any sort of unary node in the AST, which is something that happens on its own rather than needing multiple children to work, such as numbers, booleans, strings. They just know how to turn themselves into something Python could work with. Lists, very much the same. Not. Now, fun trap that I had, and I said I'd come back to this. We were testing using Faker. Is anyone here familiar with Faker? It's a great way to generate random strings of particular qualities and random values, and you can ask it for a file if you want. So we had Faker generating random variable names for parsing expressions and all the rest of it to make sure that things didn't blow up. And then we started getting random failures for one of our expressions. And it wasn't that the parser wasn't parsing it, but the value that came back out of the expression was wrong. And so I started looking at the variable names it was giving us. And they were things like notable and notice. And somebody's got it. So what had happened was, in describing our grammar, we had said not must be it can be not or not, there or not there, followed by a comparison expression. But at that point, all of our white space had been described as optional, as 0 or more white space characters. So it had seen the name and gone, oh, that's not this lookup. So that's why we now have white space and optional white space down here at the bottom of our description. That's the only place the non-optional white space is used, but it's still there as an example. Then, okay, that's not. These are here because Python's operator library doesn't actually give you add or an in because they're actually handled by the objects themselves. But otherwise, I do a dictionary mapping of whatever our operator symbol is to the operator function that will perform that on the values that it's given. And that way, for my handling of all of the operators that take 2 arguments, I can just use this one AST node to implement them. So it takes the left value, the operator, the right value, and when it's executed, it evaluates what they are, does a lookup of the operator, and returns it, and it just works. Conditional got a little clever. Functional, again, you have to register a set of functions, but once that's done, we now have a language which we can put in front of a client who is educated but not a programmer. We can allow them to write expressions with variables and lookups and calculations and tests and have them control their own output without me having to worry about somebody else coming in and using it to attack our system. All right. Any questions, please? Wow. Yes. I have some examples in README. So the way you'd use it is you import the parser, you hand it the data in a scope, and you say run, and it goes and does it. So the syntax in this particular case is we can do complex maths, we can do logical comparisons, if functions. I could probably do a live example, but they're usually not a good idea. Any other questions? The trap decorator is because I wanted to catch every time that anything blew up, I wanted to know why, and I wanted to try and catch what was going on. So I wrap every one of them in a trap decorator just to say, okay, try and do the thing, and if it fails, just wrap it up in the same error, and then I wrap it as a from. So type error and value error had specific needs. Everything else I want to come out. I want those to be kept quiet. In the back.
Where we the last?
Can we use your thing to describe regular expressions with this?
Sorry, say a little louder, please.
Can we describe regex with this type of grammar?
Theory goes that anything you can describe in a context-free grammar, you can describe in a peg. So maybe they consider, if you read the papers, that regex is a competing solution for describing pattern matching. So, but one of the examples that they give on the front page of the Parsimonious website is parsing ini files as a useful tool, which is why I thought to use JSON as well. Regex, that's an interesting idea, maybe.